All right, folks, again, I'm Damon Barnes. I'm Director of Technical Marketing for the Bluetooth SIG. So this morning, I talked a little bit earlier about the recent major enhancements to Bluetooth technology that are going to drive significant growth to Bluetooth technology over the next 5 years and beyond. And then Miko's given a little bit more detail, a couple of those recent enhancements. Now, let's talk about what's upcoming for Bluetooth in the next couple of years, and we're going to focus in on the Bluetooth High Data Throughput project that will come to fruition or complete next year. Before we go there, though, we did go through a brand refresh within the Bluetooth SIG recently. So share a couple slides with you about that, like our updated mission and all that good stuff. So in case you're not aware, the SIG, obviously we're the standards development organization for Bluetooth technology. So we oversee all things specification development, qualification, certification, trademark licensing, as well as marketing. That's where my team resides. We're the marketing arm responsible for promotion, education, evangelization of Bluetooth features. So the thing about Bluetooth, though, is that the SIG is a great organization, and we have all this responsibility, but I think our biggest value add is the developer community. You all are part of that, and so the SIG, as a company, when we rebranded, we kind of restated our mission in a way that where we talk about, we're a community of the world's most inventive companies and people collaborating to fulfill this essential need to connect, right? And so together, we're all working together to advance, promote, and protect. Got that in the wrong order. Advance, protect, and promote Bluetooth technology. So that's a little bit about the SIG and our rebrand. So now let's turn our focus to the upcoming major enhancements. So as far as the Bluetooth roadmap goes, these are what I would say are the 4 major upcoming enhancements that we have in the works. To start off with, we have the Ultra Low Latency HID project. This is a project where we're working to bring down the latency of Bluetooth LE HID devices to 1 millisecond. So this is going to bring near or close to wired performance for HID devices. There's actually going to be 2 enhancements that occur through this project. One recently released, and then the other enhancement will release next year. The target applications or use cases, of course, keyboards and mice can benefit from these enhancements, but really the main driver is going to be increasing or improving the performance of gaming controllers and XR, extended reality type solutions. But these enhancements can also benefit, I would say, industrial type applications where you need better responsiveness, you need sensors to communicate more precisely, right? So that's the Ultra Low Latency HID project. And then the next one you see listed, there's the high resolution and lossless audio projects. That's actually 2 separate projects. Both of those projects are going to work to standardize support for this really high quality audio over Bluetooth LE. Those 2 enhancements will be gated by the High Data Throughput project, which we're going to get into detail in just a moment. So skipping over that one, the 4th major roadmap item that we have is the Higher Bands project. This is a project where we're working to enable Bluetooth LE operation in higher mid-band spectrum. We're targeting 5 gigahertz and 6 gigahertz on license for the Higher Bands project. Target completion, it's a little bit out there right now, but we're estimating 2027 completion for the Higher Bands project. Now, let's turn to high data throughput. So Bluetooth High Data Throughput, this is an upcoming feature that's going to bring forth a whole new generation of Bluetooth solutions. We're going to see new silicon, more advanced software stacks, and of course, you're going to see Bluetooth in-use products that are going to gain new and enhanced capabilities. So out of the gate, of course, Bluetooth High Data Throughput is going to increase the max achievable bit rate to 7.5 megabits per second. This is going to help Bluetooth devices meet the increasing data demands across the globe. There's going to be a number of additional wireless performance enhancements or benefits that are going to be brought forth to existing applications as use cases as well. We'll get into those in just a bit on the next slide. HDT is going to also allow us, like I mentioned on the previous slide, to standardize new use cases. So high resolution, lossless audio. We're going to be able to enable multi-channel surround sound. And there's additional projects that are underway that we will share more information with the public, hopefully soon. So now let's start to look at the technological benefits that HDT is going to bring. So when we talk about the technology benefits, I mentioned already the higher data rate, so 7.5 megabits per second. We're going to be able to do this through adding support for new modulation techniques. That's going to allow us to encode more bits in every symbol that's transferred. Of course, higher data throughput, we're also going to be able to increase capacity. We're going to increase capacity around 4x. You're going to see new packet formats in a subsequent slide. We're going to be able to reduce duty cycle. And we're going to have this ability to fit multiple lower duty cycle links in a given airtime slot. So performance is going to improve, right? But we're going to be able to improve this performance and also have some options or techniques to reduce overall energy efficiency, which is really great. So I mentioned the new packet formats that are going to bring lower duty cycles. This is going to allow for more efficient use of the radio, and it's going to allow for optimization of retransmissions when data gets corrupted. And that's going to give us options for reducing energy consumption. Additionally, these new packet formats are going to allow us to divide the payloads into blocks. That's going to also give us options to reduce overall energy consumption. And then lastly, but certainly not least, HDT is going to enhance overall wireless communication reliability. You're going to see, or I'm going to talk about these new radio features that allow us to improve sensitivity. We're going to be able to improve resilience versus multipath and fading, so in challenging RF environments. And better overall wireless coexistence is going to be able to be achieved also with HDT. And then lastly, there's also going to be support for rate adaptability. So you're going to see, or I'm going to explain how these devices can actually change rate on a packet-by-packet basis with the HDT feature. So with those technological benefits covered, which all I'm sure sound really great, let's talk about how that's going to be able to be achieved in a couple of different areas. Okay, so this slide outlines what I would call like an abstracted version of the Bluetooth LE stack. The start areas are areas where the stack's going to be updated to enable support for high data throughput. The rest of this talk today is going to really be focused on the controller portion of the stack, so the bottom half. We're going to look at the physical layer. We're going to talk about the new packet structure and formats with the link layer. There's, of course, going to be new ACI commands and new events to enable HDT operation and a number of minor updates across the host. But those last 2 points are probably going to be subject best for another presentation. So now let's focus in on some of these changes that are going to be made at the physical and link layer. If I can get it to change. There we go. Okay, so Bluetooth HDT is going to introduce one new PHY. this PHY is going to support 5 new bit rates, so 2, 3, 4, 6, and 7.5 megabits per second. All are going to operate with a symbol rate of 2 megasymbols per second. The higher order modulation techniques that are going to be supported are Pi4 QPSK, 8 PSK, and 16 QAM. There's also support for coherent detection. That's going to help enable phase and frequency synchronization between transmit and receive, and that's going to help reduce the probability of errors. The diagrams that you see on the slide, those illustrate the symbol constellations for the modulation techniques. Bluetooth HDT, it's going to support forward error correction across the board. That's going to be based on convolutional coding with a half coding rate. There's also support for puncturing to enable higher coding rates for the payload zones. All right, so that was the new PHY. This slide is basically a comparison matrix of the existing PHYs and the new HDT PHY. A few points to call out here. Obviously, HDT is going to have the highest bit rate, and you compare the 2M bit rate to the 2M PHY, you see that you see that it actually has better sensitivity than, has better sensitivity than the existing GFSK PHY. Note, like I mentioned, FEC is a default for HDT. HDT is going to use the same channels and spacing as the GFSK PHYs. And like I said, HDT is going to give you the best speed and capacity out of all of the PHYs. But if you're looking for maximum range, your LE coded is still going to be your best bet. All right, so now let's turn to the link layer and the new packet structure that's developed for Bluetooth High Data Throughput. So the new packet structure includes the preamble, control header, PDU header, payload zone, and CTE. The constant tone extension, that's for direction finding information. The preamble and control header, those are going to be present or mandatory in all HDT packets. Then the PDU header, the payload zone, and CTE, those are going to be optional depending on the packet format and whether you need direction finding. I mentioned it, I think, previously, but a key new feature with HDT packets is going to be the ability to divide this payload zone into these blocks. And we'll get into that detail in a subsequent slide. Now, a quick rundown on the different zones. On the preamble, it's going to consist of a series of short training sequences and long training sequences. These short sequences are going to be used for initial calibration and for timing and frequency acquisition. That's on the receiver side. Then the long sequences allow for more accurate parameter estimation. They enable coherent detection and channel estimation, all of which is going to help improve sensitivity and performance in challenging RF environments like multipath. Then the control header, that's going to define fields that specify things like physical channel address, indicators for packet format, data rate, PDU header length, to name a few. And then on the PDU header, that's going to convey information related to packet type like transports, link IDs, payload length, presence of CTE, and really importantly, RX acknowledgements. And speaking of, since each packet signals its data rate, the transmitting device is therefore going to be able to change literally on that packet-by-packet basis, like I mentioned before. This is going to allow for adjustments based on the channel over-the-air quality, even before the retransmission of a packet. So to examine the payload zone a little bit more closely, let's look at the three new packet formats that HDT introduces. Okay, to start off with, the short format packet. This packet format is going to be used for synchronization between the devices and for acknowledgements. It's going to contain, like I said, the preamble and control header only. This short format packet is going to help reduce error time when there's no data to transmit. Also, it can be used when you only need to acknowledge consecutive whole payloads. Moving down to packet format 0, or PF0, as you'll see it denoted sometimes. This is a single payload block with a message integrity check, or MIC. The MIC, it's only going to be present if the connection is encrypted and there's no data to be transmitted. If there's no data, there's not going to be a payload zone. Then the CRC, which is the cycle redundancy check, that's for error detection. It's going to be calculated based on the sum of the PDU header, the payload block, and the MIC. And then a note on the MICs. The MICs are only going to be present for encrypted ACL connections, think the traditional Bluetooth LE type of connection, as well as connected isochronous streams and broadcast isochronous streams. Those are data transports primarily used for LE audio today, but they will have applicability beyond audio in the future. All right, so now we're to the third and most interesting packet format for HDT. This is packet format 1, and this packet format's a little bit complicated, so I'm going to attempt here to build this out step by step. Let's see how this goes. So packet format 1's the one that's going to support 4 payloads. That includes a MIC if there's an encryption. It supports payloads up to 8175 octets. Each payload plus MIC is going to be divided into blocks, 1 to 16. There's an illustration of how that looks. And so the blocks, they're going to be all the same size, but the size of each payload may be different. The CRC, that's calculated for each block. The payload zone is going to be split into intervals with a fixed number of symbols. These are called phi interval symbol streams. All phi intervals are going to be the same size except for the last one. That one can be shorter. Each phi interval is going to be followed by a terminating symbol sequence, which you see denoted as term above. The terminating symbol sequences are followed by phi interval training sequences, except for the last phi interval. The phi interval training sequences are used for data-aided tracking of phase and /or channels. A few more notes on packet format 1. So these packets, they're going to be constructed with multiple short transmission blocks, right? Each protected by their CRC. This is going to be effective for mitigating the impact of interference, and it's also efficient since you only need to retransmit the failed blocks. Also, you can selectively acknowledge part of a payload without having to acknowledge all of it. Each block, it can be acknowledged separately. This means that one block doesn't necessarily need to be retransmitted if it's corrupted. Lastly, you also don't need to transmit all the blocks in one packet. You can send, say, 4 blocks at a time and leave space for other traffic in between packets, which is really nice. One note, though, or caveat I should mention. So these blocks, they do add additional overhead. So you have the header, the CRC, and then you're going to have added link layer complexity with segment and reorder and reassembly of the blocks. So it's something to keep in mind. So I know we got into quite a bit of detail with the new packet formats, but to kind of like summarize these quickly and give you a high-level review. So your short format packet, that's going to be used for synchronization between devices and for acknowledgments. There's no payload, right? This is going to help reduce error time when there's no data to transmit, and also when there's only consecutive whole payloads that need to be acknowledged. And then packet format 0, this is going to be a really good choice to increase throughput if your application can live with 494 octet payloads or less. It's simpler to implement, and it's going to have lower overhead compared to packet format 1. However, packet format 1 with a max payload of 8175 octets is absolutely going to give you the highest throughput, the greatest efficiency, with the most robustness. I mentioned it already, but just to note again, it is going to be more complex and with higher overhead. But it's going to give you the 4 payloads in a packet. You can divide the payloads into blocks. You can take advantage of the selective acknowledgments feature, and the blocks can be spread over multiple packets. And you can take advantage of the phi intervals with phase tracking as well, the PITs. So that's the new packet structure and formats for HDT. So now to try to tie a little bit of the physical layer, link layer operation together and just kind of give you a really high-level overview of how HDT is going to operate, let me take you through this slide. So the way I explain it is something like follows. So connections, they're going to first be established via one of the GFSK PHYs. The GFSK connection may or may not be encrypted. That's up to the implementation or application. The devices will then exchange HDT features and configuration parameters. Then there's going to be a switch to the HDT PHY that happens via the PHY update procedure. Note, either the central or the peripheral device may request a change to the HDT PHY. So once these HDT connection events are in progress, going back and forth, so to speak, the HDT, the devices can rate adapt based on the link performance. So on the transmit side, each packet's going to be signaling its data rate in the control header. Then the transmitting device can also change rates on a packet-by-packet basis to adjust for channel quality. Then on the receiving side, a couple notes. So you're going to have this optional link quality feature in the PDU header that allows the receiving devices to feed back information like RSSI and SNR of the received packets. And this is going to allow the transmitting side to adjust and choose the best available HDT parameters like data rate, block size, and the like. And so that's a high-level summary of HDT operation. And now to kind of bring it all to life a little bit, Samsung was gracious enough to allow us to, actually they built this demo when the feature or specifications still a few months, several months away from being being released to the public. But they have a demonstration on their smartphone boards, and they gave us this little video excerpt. And let me try to play it here and show you the compare and contrast of a file transfer demonstration, first using the LE2M PHY, and then using the HDT PHY with a 7.5 megabits per second bit rate using packet format 1. So we're going to transfer an MP3 file. Like I said, I think it's about 2.7 megabytes in size. You'll see as this transfer is running, it takes several seconds, but we hit about 1.4 megabits per second max application data rate. It does take several seconds, like I said, but I think we're getting pretty close here, 14. Yeah, so 16 seconds to run that file transfer with the 2M PHY. Now we're going to run it with the new HDT PHY, or the upcoming HDT PHY, and it's going to go quite a... OK, it's already done. So right at 4 seconds, you transfer the same file, same 2.7 megabyte MP3 file with the new HDT PHY. So it shows you that, early implementation, but a 4x speed increase for a data transfer application. So thank you.